Chapter 4 begins to take a look at two types of functions, exponential functions and logarithmic functions, and they're very closely related as we work through this chapter. First, we're going to talk about these exponential equations that have a common base. And the whole idea behind this common base is if we have something raised to an exponent equal to that something raised to an exponent, what we can conclude is that both of those exponents are equal. It's a product of the function being 1 to 1. And so, for example, if we were asked to solve a problem such as 3 to the x equals 3 to the 7th power, because these both have the same bases, we would conclude that these exponents would also have to be equal. X to the 7th would have to be equal. X would have to equal 7. Now, we can use this same logic, though, to solve more involved problems, like, say, 5 to some power equals 125. Again, we're going to make the conclusion that if we have the same base, the exponents must be equal. We just have to do work up front to get those bases to be equal. 125, for example, could be rewritten as 5 to the 3rd power. So 5 to the 3rd power is equal to 5 to the x, and now we say, hey, those exponents, x must equal 3. And sometimes all there is to find that 5 to the 3rd power is just start dividing out. 5 goes into 125 25 times, and into 5 times. So we get 5 to the 3rd power, just factoring out that number to see what we have to work with. And we can start to make these really fun with problems such as this. How about 8 to the x equals 16? Well, 8 we can factor out to its prime factorization, which is 2 cubed. All that's to the x. And 16 we can write out as its prime factorization of 2 to the 4th. Then we'll use our exponent properties to clear the fraction. Exponent properties tell us to multiply those exponents. So we have 2 to the 3x equals 2 to the 4th power, and then we conclude that those exponents must be equal because the bases are equal. So to solve for x, we just have to divide both sides by 3, and x must equal 4 thirds. Let's try another example. How about we have 81 to the x equals 3? Well, again, the 81 we would rewrite as 3 to the 4th power, always best to go down to prime factorization, is equal to 3 to the 1st power. Multiplying those exponents, we get 3 to the 4x equals 3 to the 1st. And if the bases are equal, the exponents must also be equal. 4x equals 1. And then solve by dividing both sides by 4. X here is equal to 1/4. And we can start to make these more interesting as those exponents become more interesting. Say, for example, we had 27 to the 2x plus 3 equals 9 to the 5x minus 1. Well, we could find the prime factorizations of both parts and find out that 27 is 3 to the 3rd power to the 2x plus 3 still is equal to 9 is 3 squared, which is still to the 5x minus 1 power. We need to multiply exponents, and as we do, I want to notice we don't just multiply the 3 by the 2, we multiply it by the entire exponent. So it has to distribute through as we do this, and so we get 3 times 2, which is 6x, plus 3 times 3, which is 9, equals 3 to the, distribute the 2 onto the entire exponent, 10x minus 2. And now if the bases are equal, the exponents must also be equal to each other. So we have 6x plus 9 equals 10x minus 2. And from there, it's just a simple linear equation. Subtract the 6x's, so they're all on one side. Add 2, so the numbers are all on the same side. And we have 11 equals 4x. Divide both sides by 4, and x equals 11 fourths. Let's try one more that's interesting like that. How about we do 3 to the 5 minus x equals 9 to the x squared plus 1. 3 already is a prime factorization, so I'm just going to write it as 3 to the 5 minus x, but 9 is 3 squared to the x squared plus 1. Multiply those exponents by distributing the 2 through. We get 3 to the 5 minus x equals 3 to the 2x squared plus 2. And now if the bases are equal, the exponents must also be equal. So we have 5 minus x is equal to 2x squared plus 2. This problem having both x's and x squareds in it, we need to get everything on one side, so we'll subtract 5 and add x. Subtract 5 and add x. It's going to give us 0 equals 2x squared plus x minus 3. And we can solve that by factoring 2x times x, and a 3 and a 1. If the 1 was negative and the 3 was positive, it would be completely factored. And so we have solutions of x equals negative 3 halves, or x equals 1, by setting each factor equal to 0. So that's kind of the big idea for today. If we can get the same base on both sides, we can set the exponents equal to each other. Now there's a few things that we're going to do to make these more interesting, but really it's just going to be variations on that same thing. One thing we can look at is the fact that negative exponents make fractions. So for example, if I have 16 to the x equals 1 over 8, one side's a fraction, the other side's not. We prefer to not work with fractions. So let's keep the 16 like it is. 16, wrong color, 16 is 2 to the 4th power when we find its prime factorization. All that raised to the x. With the fraction, I'm going to write the 8 as 2 to the 3rd power, but then because it's a fraction, we'll make sure that exponent is negative. 2 to the negative 3 power, reflecting the fact that there's a fraction. So now, everything's the same. Multiply the exponents together, we get 2 to the 4x equals 2 to the negative 3. And if the bases are equal, the exponents must also be equal. 4x equals negative 3. And we solve this simple function by dividing by 4. X is negative 3/4. Let's try a couple more examples with these negative exponents. How about we do 64 to the 2x plus 3 equals 1/8 to the x minus 1. Well, 64, that's 2 to the 6th power, with the 2x plus 3 outside. 8 is 2 to the 3rd power, and to make it a fraction, 1 over 8, we need a negative exponent. And that's all to the x minus 1 power. Now we can take those exponents through the parentheses. Multiplying, distributing, all the way through gives us 2 to the 12x plus 18 equals, taking that negative 3 all the way through, 2 to the negative 3x plus 3. And again, since the bases are equal, the exponents must be equal to each other. 12x plus 18 must equal negative 3x plus 3. And then solve the simple linear equation. We'll add 3x to both sides to get all the x's on the same side. We'll subtract 18 from both sides to get all the numbers on the other side. And we have 15x equals negative 15. So when we divide both sides by 15, x is equal to negative 1. Let's do one last example with these fractions and negative exponents. How about we do 25 over 9 to the x equals 27 over 125. What I want to notice is 25 is 5 squared. And 9 is 3 squared. Because they're both squared, what we're going to do is say that the entire fraction then must be squared times the x. 27 is 3 to the third, and 125 is 5 to the third. Because they're both cubed, we're going to say the entire fraction is just cubed. However, what I want to notice is both sides here are not identical. One side is 5/3, the other side is 3/5. They're close, but close only matters in horseshoes, scud missiles, and slow dancing, not in math. The way we flip a fraction over, though, to make them the same, is we use a negative exponent. And we can make either side negative. I'm just going to do the left side. So we're going to do 3/5 to the negative 2x equals 3/5 to the third power. Probably should have done that in green. That's okay. Now with the same base, we say the exponents must be equal. Divide both sides by negative 2, and x is equal to negative 3/2. So that's the first variation on a theme. Negative exponents give us reciprocals if that's what we desire. We also may need to, along the way, use some exponent properties. For example, if we've got 5 to the x squared equals 25 to the x times 125. We could write each part with a base of 5. 5 to the x squared equals 5 squared to the x times 5 to the third. And then we know to multiply our exponents together, so we have 5 to the x squared. Whoops. When I multiplied my exponents, I accidentally deleted. Multiply those exponents together, so we get 5 to the x squared equals 5 to the 2x times 5 to the third. But we've got double 5 on the right side, and that's not going to work. Order of operations says we cannot treat that like it's a 25, 5 times 5. Order of operations says we have to deal with exponents before we do any multiplication. However, we do have an exponent property that says a to the m times a to the n, same base, we add the exponents. And that's exactly what we're going to do here. 5 to the x squared equals 5 to the 2x plus 3. Now that we have the same base, we can say the exponents must be equal. X squared equals 2x plus 3. Because we have x squared and x, we want to get this thing equal to 0, so we'll subtract 2x and we'll subtract 3 from both sides. So 0 equals x squared minus 2x minus 3. Factor that to x minus 3, x plus 1. And x is equal to positive 3 or negative 1. So in this case, we had to use the exponent property to get the common base on the right side. Let's look at one more example where we do that. Let's do 27 to the x squared over 81 to the x equals 1/3. And by looking at this, you might guess our common base is in fact 3. 27 is 3 to the 3rd power to the x squared. Over 81 is 3 to the 4th power to the x. Equals 1/3 is 3 to the negative 1 power. Remember, the exponent creates the fraction. We then need to multiply our exponents together, giving us 3 to the 3x squared over 3 to the 4x equals 3 to the negative 1. And again, this time on the left, we've got a double 3. This time the double 3 comes from division. And you remember the exponent property that when we're dividing with the common base, what we do is we will subtract those exponents. So let's do just that. We have 3 to the 3x squared minus the 4x equals 3 to the negative 1. And now that we have a common base, we say the exponents must be equal. 3x squared minus 4x must equal negative 1. Add 1 to both sides. 3x squared minus 4x plus 1 equals 0. Factoring 3x minus 1, x minus 1, and then set each factor equal to 0 to give us x equals 1/3 and 1 for our final solution. So as this problem illustrates, sometimes the exponent properties of adding or subtracting exponents are going to help us to get rid of the base and focus on the exponent. I want to show you one last trick that does come up on several problems. It makes for an interesting trick to solve, and that's when these exponent problems are quadratic in form. For example, if we have 3 to the x plus 9 times 3 to the negative x equals 10. And my color coding system is going out the door on this problem because it's going to be too many steps. But what's interesting here is that 3 to the negative x can become a small fraction. 9 over 3 to the x equals 10. And then we know we can clear a fraction in an equation by multiplying by that common denominator. So what we're going to do is multiply each term by 3 to the x. 3 to the x. 3 to the x. And when we do, you notice that 3 to the x is there twice, so we have 3 to the x squared. Plus, we have a plus 9, equals 10 times 3 to the x. And if you think about this almost as a composition, as a function inside a function, the 3 to the x is our variable as we factor and solve this. Because we have a 3 to the x and a 3 to the x squared. So we'll subtract 10 times 3 to the x from both sides. And that gives us 3 to the x squared minus 10, 3 to the x's, plus 9 equals 0. And we can factor. 3 to the x squared is 3 to the x times 3 to the x. We get the 9 by subtracting 9 and subtracting 1. So we end up with 3 to the x equals 9 when we add 9, or 3 to the x equals 1 when we add 1 to both sides. And now both of these have become just like one of the problems that we started with just 20 minutes ago. Now we're going to rewrite each of these with a common base of 3. 9 is 3 squared. 1 is 3 to the 0 power. Anything to the 0 power is 1. And so we set our exponents equal. X equals 2 or x equals 0. We have our two solutions. Let's take a look at one last problem. How about 49 to the x squared minus 2 minus 8 times 7 to the x squared minus 2 plus 7 equals 0. I want to notice that it almost looks quadratic in form if that 7 to the x squared minus 2 was our variable. And we can accomplish that if the 49 is rewritten as 7 squared. Let's write that, though, as 7 to the x squared minus 2, and we'll put the squared outside of parentheses, because the order of the multiplication won't matter. Minus 8 times 7 to the x squared minus 2 plus 7 equals 0. And then we can factor. We have 7 to the x squared minus 2 times 7 to the x squared minus 2. And the 7 is 7 times 1, and they're both negative. Which means we can set each factor equal to 0 and add 7. So 7 to the x squared minus 2 equals 7. Or add 1, 7 to the x squared minus 2 equals 1. And rewrite each equation with a common base. The first one's easy. It's essentially done for us. That's 7 to the first power. The second one, 1 is 7 to the 0 power, because anything to the 0 power is 1. And so we can say the exponents must be equal. X squared minus 2 equals 1, or x squared minus 2 equals 0, and solve each equation. First, by adding 2, we get x squared equals 3, or x squared equals 2, and then when we take the square root of both sides, don't forget your plus or minus, square root of 3, or plus or minus square root of 2. And we have our solutions. The idea behind all these problems is exactly the same. These exponential equations, if you can get them both sides to have a common base, we can end up solving them by setting the exponents equal to each other. We want to be really good and comfortable with these exponents with a common base so that we can start to transition then to what we do when we can't get a common base. And as you might guess, more often than not, it's impossible to get that common base. And so we're going to have to use some other strategies. But this strategy is nice. When it works, it's a lot faster. So take a look at the homework. We will see you in class. In our video yesterday, we took a look at how we could solve equations with exponents by getting a common base and setting the exponents equal. We also concluded by saying that we can't always get a common base. Sometimes we need a different strategy, and to set up that different strategy is what we're going to do today. And then tomorrow, we'll look at how we can use this different strategy in order to solve exponential equations with different bases. But first, we have to understand what logarithms are and their properties and how we can use them. So to start off with, we're going to look at the definition of exactly what a logarithm is. A log is an exponent. Simply put, it's how we solve for the exponent. If we've got some type of base raised to some exponent that is equal to some type of answer, we can rewrite this problem, exactly the same problem, using what's called a log. We will put a subscript of the base and we will stick the answer in there. And it will always be equal to the exponent. Because a log is an exponent. The log will equal whatever the exponent is. So for example, if 7 squared equals 49, then we could rewrite this as a log with a base of 7 of 49 would be equal to that exponent of 2. Both of these are expressing the same information, but one is solved for the exponent. The exponent 2 is equal to log base 7 of 49. The other one is solved for the solution. 49 is equal to 7 squared. But each form has its advantages. We can also switch back the other way. I could tell you that log base 5 of 7 equals a. And you could rewrite this as an exponent problem because 5 is the base. The exponent is what the log equals. A is equal to 7. The most essential thing you should be able to do and understand is how to switch back and forth between log notation and exponent notation. Because sometimes a problem is easy in log notation and hard in exponent notation. Or sometimes it's easy in exponent notation and hard in log notation. So when we hit a brick wall in one form or the other, we'll switch to the other form. Because generally the other form will always be easier. So let's first look at how we can evaluate a log. If I want to know what log base 6 of 216 equals, the way we're going to evaluate logs is we are going to rewrite as, actually no, better said, first we're going to make it equal to x, and then change to an exponent. In other words, if we want to know what log base 6 of 216 equals, for now we're going to say it's equal to x. And whenever we get our solution for x, that must be what log base 6 of 216 is. So first we will rewrite it as an exponent. 6 to the x power is equal to 216. Well, the nice part about 216 is we know that's 6 to the 3rd power. And so we've got the same base on each side, and as we've seen before, we just set the exponents equal. So x is equal to 3, or log base 6 of 216 is equal to 3. We can even take a look at what is log base 2 of log base 5 of 25. Well, first starting inside parentheses, because that's what order of operations tells us to do, log base 25 of 25, we make that equal to x. And when we change this to an exponent, we have 5 to the x equals 25. And 25 we know is 5 squared. And so the exponents must be equal, x must equal 2. Which means that all this stuff in the parentheses must equal 2. Which means log base 2 of log base 5 of 25 is really saying log base 2 of the answer we just found of 2. So maybe we should say log base 2 of 2 equals x, and do it again. The base of 2 to the x equals 2. Well, g, make those exponents equal to 1, equal to each other. X equals 1. So log base 2 of log base 5 of 25 must equal 1. We can even do this with some ugly looking things, but the process should still be the same. If we have log base the square root of 3 of 1 over 27, we want to know what that equals. So for now, we'll make it equal to x. Rewrite it as an exponent. We have the square root of 3 to the x equals 1 over 27. And we can get both of these to have the same base because square root is really just a 1/2 power. So we have 3 to the 1/2 x, and 27 is 3 to the 3rd. We make it a fraction by making it a negative third. Then we can take our exponents and make them equal to each other. 1/2 x equals negative 3. And solve by multiplying both sides by 2, and x equals negative 6. So log base square root of 3 of 1/27 is equal to negative 6. Similar to how we evaluate logs is how we solve a simple log equation. And that is we're going to convert to an exponent problem. The way we're going to solve these is we're going to convert to exponents. So let's take a look at an example. Let's do log base 4 of x equals 3. Can't solve it as a log, so let's change it to an exponent problem. 4 is the base, 3 is the exponent, equals x. Well, 4 to the 3rd, that's easy, that's just 64, equals x, and we solved the log equation. It's pretty much the process we're going to go through to solve these simple log problems. If we have log base 2 of 3x plus 5 equals 4, can't solve it as a log, so we'll change it to an exponent problem. 2 is the base, 4 is the exponent, equal to the 3x plus 5. And then we just solve from here. 2 to the 4th is 16, equal to 3x plus 5. Subtract 5, and we have 11 equals 3x. And divide by 3, x is 11/3. It's pretty simple to solve these log equations. Again, the most important thing you can do with logs is convert between logs and exponents. exponents, and logs. You should be able to do that without hesitation, without any doubt in your mind about how it's done. More interesting to us, though, in this college level class is how we do the properties of logarithms to help us do some more advanced things. The first 4 properties we're going to see if we can figure out intuitively. So the first one is going to be the log base anything of 1. What's that going to equal? Well, let's think about it over to the side here. If we said the log base anything of 1 and made that equal to x, we'd be saying a to the x equals 1. What exponent will always give us an answer of 1? Anything to the 0 power is always equal to 1. So the log of 1 will always be equal to the exponent of 0. That's our first property you should know. The other one we should know is the log of base anything of anything. What does that equal? Well, if we think about that, we're saying log base anything of anything, we'll make that equal to x. And so we'll say that anything to the x is equal to anything. If we make that exponent 1, we see that x is equal to 1. When the base of the log is the same as the base of the problem, they're inverse operations, essentially. They undo each other, leaving just the 1 behind. Which kind of leads to log base a anything of that same thing to the x power. Essentially, we're saying log base anything of a to the x is equal to some unknown x. Well, if we rewrite this with a as the base and x as the exponent, a to the x equals a to the x. The exponents must be equal. This just equals x. Because the base of the exponent and the base of the logs are the same, the solution is just going to be the exponent. And one we don't see very often, but it works much the same way as if we have a base with a log base a of x. Again, the base of the exponent and the base of the log are the same, so we're just left with the guts of x. So these are the 4 basic primary properties that you should know about logs. The next 3 are not as intuitive, but they kind of make sense when we play with them. So let's play with them. We're going to play first, and then I'll tell you what the answer is after we're done playing. We're going to say, let's say u is equal to a to the r power. And w is equal to a to the s power. So if we were to change these into logs, the first one would be log base a of u equals the exponent r. And the second one would be log base a of w equals, I don't like doing s. Let's not do s. Let's do t. A to the t. That way it doesn't look like a 5. So as we play, we're going to look at what happens when we multiply u times w. Now, u times w is essentially saying a to the r times a to the t. And what we know about exponents is we can add exponents r plus t together. So u times w is equal to a to the r plus t. Let's rewrite this as an exponent, as a logarithm property. If we wrote this as a log, the base you see is a, and uw is what's inside the log, and it will equal the exponent r plus t. And here's the rub. The important conclusion is r is log base a of u. Plus t is log base a of w. Which means log base a of u w is equal to log base a of u plus the log base a of w. This is our important fifth property. What this property is essentially saying is if we're multiplying two things inside the log, u times w, are multiplied inside the log, it can be rewritten as a sum of two logs. And that makes sense, because we know that if we multiply two bases, we add the exponents. And the logs are the two exponents being added together. We can do a real similar exercise. We'll call this number 6. Again, with our plane, we're saying u equals a to the r. We're saying that w equals a to the t, which means if we change these into logs again, it would be log base a of u equals r, and log base a of w would equal t. But this time, instead of multiplying u times w, I'm going to divide u divided by w. Which means we're really taking a to the r divided by a to the t. And again, our exponent properties then tell us that we should subtract those exponents. So that's a to the r minus t. And then if we convert this to a log again, the base is a of u over w. It's going to equal the exponent r minus t. But again, we know that r is log base a of u. And t is log base a of w. So we get this new property that log base a of u over w is equal to the log of u plus the log of w. In other words, if we're dividing two things inside a log, whoops, big mistake there. It was a minus in the problem. It should still be a minus. There we go. Minus, minus, minus. It was r minus t. If we're dividing two things inside a log, it's the same as subtracting two individual logs. Which makes sense if you think about it on several levels. With exponents, we know if we're dividing two bases, we subtract the exponents. Logs are exponents. So dividing two pieces means we subtract the two pieces in individual logs. Another thing that makes sense is a negative log, the second piece, a negative log, you could think about as a negative exponents. And where do negative exponents end up? On the bottom of a fraction. So this property just makes sense all around when you think about it in terms of the fact that a log is an exponent. Negative exponents go on the bottom. Division, we subtract exponents. It just all works. Here's one more. This one we're just going to do a single u is equal to a to the r power. And we're going to rewrite this as a log base a of u equals the exponent of r. Did I mention we're doing a lot of changing between logs and exponents and logs? Did I mention that that's the most important thing you can do after this lesson? Okay, good. So here, I'm going to start with u, and I'm going to raise it to a constant, u to the c power. Doesn't matter, some exponent. Well, that means I'm really taking a to the r and raising it to some exponent. We have an exponent property that says we can multiply those two parts together, those two exponents. We really have a to the CR. I'm just going to put it alphabetically. So if we rewrite this as a log, we want to make the base a. So log base a of the other side, which would be u to the c, must be equal to the exponent on our base, which is CR. So you can see if we rewrote this, it would be a to the CR equals u to the c. We could have written it another way with a base of u, but we've been kind of on this theme of base a, so I want to stick with this base a theme. What's nice about this is r, we remember, is equal to log base a of u. And so this gives us log base a of u to the c is equal to c times log base a of u. And this becomes our seventh important property. And the important property, what we're often going to see it called, is we're going to grab that exponent inside the log and move it out front. Exponents inside the log can move out front as multiplication. And that makes sense, because if we have an exponent inside of an exponent, because a log is an exponent, we multiply those together. So multiply the exponent times the log times the other exponent. Something we can never do, though. I see this all the time on test. Someone's going to do this on our test. Don't let this be you. Someone will say the log of a plus or minus b, it doesn't matter, and they will say, hey, I got an idea. Let's distribute the log. They say log of a plus or minus, depending on the sign, log of b, because they distribute the log. That does not work. How do I stress this enough? You cannot do that. Cannot do that. First off, the idea of distributing the log does not work, because log is an operation. It's not times log. Log is an operation. That's like distributing plus, or distributing square root, or distributing cube, which people do all the time. That's bad too. Log is an operation. You can't distribute it. We're not saying log times a plus b. We're saying the log of a plus b. It's function notation is what it really is. It's saying f of a plus b, where the log is the function. Do not distribute the log. There is no such property. I make a big deal about it now. Someone's going to do it on the homework. Someone's going to do it in class. And someone's going to do it on the test. Don't do it. Log cannot distribute. Okay. Off my soapbox. Let's do some examples where we can use these properties. We're going to write as a single log. One advantage of these properties is if we have a lot of logs that are added and subtracted together, we can squish them together into a single logarithm that's easier to work with. For example, if we've got log base 2 of a plus log base 2 of b minus log base 2 of c. We can squish these three logs using our properties into a single logarithm. First, we'll write it as a log base 2. They all have to be base 2. Then inside the log, one thing I like to think about is positive logs are positive exponents. They're going to end up in the numerator. Negative logs are negative exponents. They're going to end up in the denominator. So the a and the b are positive. Added together, they get multiplied in the numerator. The c is a negative log, and so that's going to end up in the denominator. We can compact log A plus log B minus log C together into log of A times B divided by C. We can add an extra step to this and say, how about 4 log base 7 of A minus 2 log base 7 of C plus 5 log base 7 of D minus 1/2 log base 7 of X. First, before we squish all these together into a single log, we've got all these coefficients out front that are going to make life difficult to work with. But we have a property that says those coefficients out front can double as exponents inside. So this is the same as log base 7 of a to the 4th minus log base 7 of c squared plus log base 7 of d to the 5th minus log base 7 of x to the 1/2. And in fact, that 1/2 is better expressed as a square root. 1/2 power, remember, the index is the denominator of the fraction. Now we can write these all as a single log base 7, where positive exponents are multiplied in the numerator and negative exponents are multiplied in the denominator. So we have a positive a to the 4th, a negative c squared, a positive d to the 5th, and a negative square root of the x. Might be tempted to rationalize that denominator, but I'm going to let you be lazy on this problem today, and we will stop there at log base 7 of a to the 4th, d to the 5th, over c squared square root of x. We've squished this down and combined it to a single logarithm. We can go the other way too. We can expand logs and write them out as many, many, many logs. In fact, in actual application, this is the way that you prefer to go usually. And I'll show you some examples of this, where we take one log and we stretch it out into many logs that are easier to work with, or that we know stuff about. So for example, if we have log base 5 of a squared b cubed over cd, we could expand this out so that each factor gets its own log. So we're going to do a log base 5 of the a squared plus, because it's positive, it's in the middle, numerator, log base 5 of b cubed. The c and d are in the denominator. They're negative exponents, so they're negative logs. Negative log base 5 of c, negative log base 5 of d. And we can complete this expanding process by grabbing those exponents and moving them out front. Grabbing those exponents and moving them out front. Actually, this process of grabbing an exponent and moving it out front is going to be essential for what we're doing tomorrow. We've got 2 log base 5 of a plus 3 log base 5 of b minus log base 5 of c minus log base 5 of d. And we have our expanded logarithm. Let's do one more example where we're expanding. Let's expand log base 3 of 9a square root of b over c cubed d. Again, each factor gets its own logs. Positive logs mean numerators. Negative logs, like negative exponents, mean denominators. So going across the top, we have a log base 3 of 9 plus, still in the numerator, a log base 3 of a, plus a log base 3 of the square root of b. And I'm going to change that to an exponent, b to the 1/2, because as you might have guessed, we're going to play with exponents in a minute. The c cubed d is in the numerator, so we're going to subtract log base 3 of c cubed, and subtract, because it's still in the denominator, log base 3 of d. One more piece I want to play with is that 9. If we were to factor the 9, that would be 3 squared. Which is interesting because this now, log base 3 of 3 squared, is one of our properties that we saw at the very beginning of our properties discussion. Number 3, if the base matches the base, the answer's the exponent. So log base 3 of 3 squared, the answer is the exponent of 2. Plus, we can't do anything with log base 3 of a. Plus, we can grab that 1/2 exponent and move it out front. 1/2 log base 3 of b. Minus, we can grab that 3 exponent and move it out front. 3 log base 3 of c minus log base 3 of d. And in this way, we're allowed to expand our exponents. Why on earth would you want to expand your exponents like this? Well, let's take a travel down memory lane, back to the dark ages, before things like Google and text messaging and Instagram. Back to the days where we were asked to find logarithms by hand. There were no calculators that would calculate logarithms for us. You might notice your calculator has a log button on it. We're going to talk about how to use that button tomorrow. For today, though, we're going to talk about how they used to do it. And they used to have these books just full of tables called log tables. And these log tables would tell us the approximate value of various logs. It might say the log of some base, we're going to call our base a, of 2 equals 0.45. It would say that the log of this same base of 3 equals 0.72. It would say the log of this same base of 5 equals 0.97. And what you notice I've done is I skipped the number 4. In fact, I also skipped a lot of fractions and decimals. What the tables would give us is only the logs of the prime numbers. And then we would have to use the prime numbers by hand in order to calculate these other log values. For example, if we want to know what the log base a of 18 was equal to, we would say, well, 18, let's factor it. That's 2 times 9. Well, 9 is 3 times 3. So really, log base a of 18 is log base a of 2 times 3 squared. So let's take this multiplication problem and let's expand it. Let's write a log for each individual factor. We can do a log base a of 2 plus the log base a of 3 squared. In fact, we would continue simplifying by grabbing that squared and moving it out front. So we have log base a of 2 plus 2 log base a of 3. And now we're able to calculate what this equals. Because we know the log of 2 is 0.45. Plus 2 times, we know the log of 3 is 0.72. So the log of 18 is 0.45 plus 2 times 0.72, which is 1.89. We've now calculated what the log of 18 is. And we can use this pattern on any type of logarithm. We can even do it, let's do log base a of a fraction. How about 10/3? Well, that would be the log base a of 10 is 2 times 5 over 3. And so we would rewrite this as an expanded logarithm. We'll do a log for the 2 plus the log for the 5 minus, because it's in the denominator, denominators are negative exponents, log base a of 3. And I'm running out of space on my board. But we see that log base a of 2 is equal to 0.45 plus log base a of 5 is 0.97 minus log base a of 3 is 0.72. And so 0.45 plus 0.97 minus 0.72 is 0.7. So off my screen, it equals 0.7. We now have our solution. The log of 10/3 is 0.7. Let's do one last example of these. You should have those written down in your notes. I'm not going to keep scrolling up and down. Log 2 is 0.45, log 3 is 0.72, log 5 is 0.97. We're going to find log base a of 8, a to the 5th. Again, we need to rewrite that 8 in its prime factorization form, because it's the prime numbers that are going to be in our table. 8 is 2 cubed times a to the 5th. And so when we write this as 2 logs, we'll write it as log base a of 2 to the 3rd plus log base a of a to the 5th. Well, we know the 3 can move out front. So we have 3 log base a of 2 plus, we should also know that log base a of a to the 5th is 5, because the base of the log matches the base of the problem, so the solution is the exponent. And so the only substitution that really needs to be made is the log of 2. And we wrote down that the log of 2 is 0.45 plus 5. And so to get our answer, we do 3 times 0.45 plus 5. We get 6.35. And so in this way, we're able to find out a solution for these various logs that are not in our log table. And that's how we used to calculate them, before calculators. Today, however, we have calculators, and life's a little bit easier. But it can't be super easy. It would take far too much work to program your calculator to do every type of log possible. Log base 1, log base 2, log base 3, log base 4, log base 5. It would take a lot of time and energy. So we have a solution. We only put 2 logs on your calculator. We'll talk about the 2 logs in class or during the video tomorrow for the 4.3 section. But for now, we're going to talk about how we can take any log and change the base to match the base that we want. So tomorrow, we're going to want the base our calculator can do. For now, we'll talk about how we can change any base. And to set this up, we're going to consider some base to an exponent equals an answer. There's 2 ways that we can play with this. One way is going to set up what we're going to see tomorrow. The other way we've seen already. The way we've seen already over here on the right is we just change it to a log problem. We say the log base b of a equals the exponent x. But what if instead we had done something completely and entirely different? What if we had taken the log base c of both sides. A different base, a new base. The log base c of b to the x equals the log base c of a. Because I can do anything to both sides of the equation, and it's still equal, right? So, grab that exponent and pull it out front. X equals log base c of b, which is equal to log base c of a. Get x alone by dividing both sides by log base c of b. And x is equal to log base c of a over log base c of b. Here's where we get our formula. Notice originally we said x was equal to log base b of a. But after our plane, we said it was also equal to log base c of a divided by log base c of b. So when we combine that together, we get log base b of a is equal to the log of a different base of a divided by log base c of b. This is our final property. It should have probably been included in our property list earlier, but it just fits into the discussion better here. We can change from base b to base c by dividing what's inside the log by the base of the overall log in two separate logs. So in other words, if we wanted to write log base 5 of 73 with a base 10, we'll say 2 base 10, we would say log base 10 of the 73 of the inside stuff divided by log base 10 of the base, which is 5. And this now has the exact same value, but we've changed the base from base 5 to base 10. Let's do one more example where we see this happen. Let's take log base 2 of 36, and we're going to convert it to base 9, just for kicks. Well, we would now have a log base 9 of the answer, of the stuff inside, of the 36, and we would divide by log base 9 of the base of 2. And this would have the exact same value. That changes the base on the log. So we've looked at a lot of things today, really going over the properties of logarithms. First thing you need to know is how to change a log and an exponent between each other. A base to an exponent equals a, or log base b of a equals the exponent. You need to know how to do that. Second, we said the log base anything of 1 is always 0, because anything to the 0 is 1. We said the log base anything of that is always equal to 1, and that really comes off of the fact that the exponent is 1. So more generally, the log base anything of anything to an exponent is equal to that exponent. Technically, we can switch this around and say anything to a log base anything of x is also equal to x. They're inverses. Logs and exponents are inverses. They undo each other, giving just the inside. After 5 comes 6. We said that the log base anything of a product is equal to the log of the first one plus the log of the second one. Similarly, the log base anything of a quotient is equal to the log of the first one minus the log of the second one. Or how I like to think about it is negative exponents go on the bottom, positive exponents on the top. And finally, the last property we saw was the log base a of b. We can change the base to any other base we want of the stuff divided by the log of the base. Those 8 properties are what we really look at working with in today. We want to be really good at these properties so we can start to manipulate the logs to actually do stuff with them. That stuff we want to do involves solving equations, involves setting up application problems. Lots of great stuff. So take a look at the assignment today, and we will see you in class tomorrow. Now that we have gotten good with what a logarithm is and how to use logarithms, we're now ready to solve the problem that we started with at the beginning of this chapter. At the beginning of this chapter, we found that we were able to solve problems with the variable in the exponent by getting a common base on both sides. And if they both had a common base, we could set the exponents equal. So then the logical question from there is, what if I can't get a common base? What if I can't get the same base on both sides? How do I solve that problem? And as you might imagine, this is more often the case than not. So to set this up, we had to talk about logs yesterday, and today we're finally ready to answer that question. And first I want to talk a bit about these things called natural and common logs. Natural logs and common logs. The first one is the common log, and that is a log with a base of 10. We use these a lot in science, especially with scientific notation. Scientific notation is always times 10 to some power. So base 10 is a pretty common base. And so to save us some work, this base is going to be unwritten. In other words, if we've got, let's say, 10 to the third power equals 1,000. And we wanted to write this in a log form. We would write this as log base 10, which we would not write, of 1,000 is equal to 3. So whenever we do not see a base written, we will always assume it's a base 10. And in fact, whenever we have a base 10, we won't write it. So we are now ready to solve problems like 10 to some power equals maybe 18. If I were to change this to a logarithm, I wouldn't write the base. I would just write log, because it implies a base 10 of 18 equals x. And what's nice about log 18 equals x is I can do log 18 on my calculator. What I'll notice on my calculator is there is a log button right next to the 7. No base is written. So that assumes the base is 10. So we can type in log 18 and close the parentheses. And when we hit enter, we find out the value for that. Our value for x is 1.255. 1.255. And we rounded down, so it's going to be a little bit less than we wanted. But if we wanted to check that answer, 10 to the x, 10 to the 2, because that equals x, 10 to the 1.255 power on our calculator, 10 raised to the 1.255 power, oops, I got an extra 1 in there. So 10 to the 1.255 power, hit enter, and it's 17.98. If you round that up, it's 18. And because we rounded our exponent down, we ended up rounding down the answer. But it's essentially, if we round it just to the tenth place even, 18.0. So that's our first natural log, a base 10. It is unwritten. I'm sorry, that's our common log. The natural log is a different base. The natural log is a base, what we're going to call E. And E stands for Euler's constant. Euler is spelled E-U-L-E-R. Euler. You don't need to know that, though. And E is kind of like pi in that we use it to estimate a number that has no pattern, no repetition. E is approximately 2.7183, and it goes on and on and on forever with no pattern. It is going to be written as Ln, standing for log natural. In Italian, the nouns and the verbs and the adjectives are in a different order than English, so the L comes first. Log natural, meaning natural log implies the base is E. And E is an interesting one because it kind of comes up naturally all over the place. It comes up in population growth of bacteria. It comes up in decay and radioactive decay and carbon dating. It comes up in finances and how your bank account grows. It comes up in all these different natural places. And because it comes up so often, we do the abbreviation for it. So, for example, if we had E, let's do it in blue again. If we had E cubed, and if we were to figure out what E cubed was, we'd come up with about 20.08, 0.09 really, rounded. And we would have changed this into a log. We would use a natural log of the 20.09 would equal the exponent of 3. So no base written. Natural log implies the base is E. And that allows us to solve problems like e to the x equals 35. Because we have to just change that to a log, and because the base is e, we'll write it's a natural log of 35 is equal to the x. And what you may have noticed on your calculator is right next to the number 4, underneath the log base 10 is the natural log button. So we can do a natural log of 35 and find out our x is 3.56. Well, 55. Let's go 555. So x is equal to 3.555. And again, if we were to test this in our calculator to make sure it's right, e to the 3.555, again, we rounded down, so we're going to end up a bit too small. The way we get the e is we hit second, and then above the ln, you see it says e to the x, and type in the 3.555, an extra 3 again, 3.555, should be just shy of 35, and indeed if we round to the 10th place it would be 35.0. So we can take a base 10 or a base e and type those into our calculators. We are going to use base e more often, the natural log, unless it's convenient to go with a base 10, because it's going to be more useful to us when we get to calculus. So let's try a few examples where we're going to solve these problems that have the wrong bases. And the way we solve them is we are going to take the log, preferably the natural log, of both sides. So for example, if we want to know 5 to what power equals 9, we're going to take a natural log of both sides, ln, ln. So we have the natural log of 5 to the x equals the natural log of 9. And what's nice about this is we know that this exponent inside the log can move out front. So we have x ln of 5 equals the ln of 9. We want to solve for x. We want to get that x alone. It's x times the natural log of 5, so we'll divide both sides by the natural log of 5. And x is equal to whatever the natural log of 9 is, divided by the natural log of 5, and our calculators can help fill in the blank from there. Natural log of 9. Make sure you close the parentheses after your natural log. Very important step. Divide by natural log of 5. For some reason I'm hitting the button twice. There we go. Natural log of 9 divided by natural log of 5 is 1.365. 1.365. And if we were to check it, 5 to the 1.365 power is approximately equal to 9. Now we can start to make these problems a little more interesting, a little more exciting, by saying something like 3 to the 2x minus 4 equals 6. And again, anytime we want to get an exponent out, a variable out of the exponent, we'll take the natural log of both sides, because we can do anything to both sides of an equation. When we do, we have the natural log of 3 to the 2x minus 4 equals the natural log of 6. Now our exponent that's inside the log can come out front. We want to make sure that entire exponent comes out front, so we have to put it in parentheses as we do so. 2x minus 4 times the natural log of 3 equals the natural log of 6. Several ways we can solve from here. I'm going to go ahead and just distribute the natural log. So that's going to give us 2x natural log of 3 minus 4 natural log of 3 equals the natural log of 6. Thinking back to Unit 1 when we were solving our formulas for a variable, we're solving for x. We want to get everything without an x on the other side. So we'll add 4 natural log of 3 to both sides. 2x natural log of 3 equals the natural log of 6 plus 4 natural log of 3. Almost done. To get x alone, we divide by everything it's multiplied by. Divide by 2 natural log of 3 on both sides. The natural log of 3 and the 2's go away. So x is equal to the natural log of 6 plus 4 natural log of 3 over 2 natural log of 3. And our calculator can do all the work from here. As long as we're careful. First thing we need to be careful of is every time we hit the natural log button, it's going to open up parentheses. Automatically. Make sure you close the parentheses every time. Another thing to be aware of is to make sure the computer or the calculator knows that it's a fraction. Put the entire numerator and the entire denominator in parentheses. So parentheses for the numerator, natural log of 6, close the parentheses, plus 4 natural log of 3, close the parentheses, and then close the parentheses again for the numerator. Divided by, open a parentheses for the denominator, 2 natural log of 3, close the parentheses on the natural log, close the parentheses on the denominator, and our x, our solution, is 2.815. 2.815. Let's try another example. Number 3, we're going to do 7 to the x equals 9 to the x. What exponent gives the same answer for both a base of 7 and a base of 9? Well, to get the variable out of the exponent, we'll take a natural log of both sides. Natural log of 7 to the x equals natural log of 9 to the x. And what's nice here is this grabs those exponents and moves them in front of their logarithm. So we have x natural log of 7 equals x natural log of 9. Thinking back to when we solved our linear equations, we need to get all the variables on the same side. So let's subtract x natural log of 9 from both sides. When we do, we get x natural log of 7 minus x natural log of 9 equals, anything minus itself is always 0. And then we know once we have all the x's on one side, we can factor out that x, leaving behind natural log of 7 minus natural log of 9 equals 0. It's x times that stuff. So to figure out what x equals, we divide by that factor of natural log of 7 minus natural log of 9. And this one's really nice because it just leaves x on the left, and 0 divided by anything is 0, so x equals 0. And sure enough, if you think about this, we probably should have known this at the beginning. 7 to the 0 is equal to 9 to the 0, because anything to the 0 power is always 1. But it was a real nice exercise to go through all that step to set up our last example. These make great test type problems. 3 to the 2x plus 4 equals 5 to the x minus 6. Again, we want to get the variable out of the exponent. We cannot get the same base on both sides. So we'll solve by taking the natural log of both sides. Gives us the natural log of 3 to the 2x plus 4 equals the natural log of 5 to the x minus 6. Once we see an exponent inside of a logarithm, our first instinct should always be to move it out front of the log. In parentheses, is signifying the entire exponent's been moved out together, 2x plus 4 times the natural log of 3 equals x minus 6 times the natural log of 5. We have fewer options for solving here. We need to get rid of these parentheses. So let's distribute through the parentheses just like we did last time, giving us 2x natural log of 3 plus 4 natural log of 3 equals x natural log of 5 minus 6 natural log of 5. Now we're just solving a linear equation. We need to get the variables all on one side and everything without a variable on the other side. So let's move the variables to the left. We'll subtract x natural log of 5 from both sides. Then the 4 natural log of 3 has no variables, so we'll subtract it out as well. Subtract 4 natural log of 3. So we have 2x natural log of 3 minus x natural log of 5 equals negative 6 natural log of 5 minus 4 natural log of 3. Since we have the x's all alone on one side, we can now factor it out, leaving behind 2 natural log of 3 minus the natural log of 5, still equal to negative 6 natural log of 5 minus 4 natural log of 3. Finally, to get the x alone, we divide by what it's multiplied by. Divide by 2 natural log of 3 minus the natural log of 5 on both sides. And that leaves behind just our x is equal to negative 6 natural log of 5 minus 4 natural log of 3 over 2 natural log of 3 minus natural log of 5. And while it got ugly, the process was very simple pattern that we saw in Unit 1. Get all the variables on one side, factor out the x, and divide. Now when we type it in our calculator, we're going to have to be careful. First, the numerator and denominator must go in parentheses, so the calculator knows there's more than one piece to the fraction. Also remember, every time we hit the natural log button, it's going to automatically open up a parentheses. Make sure you close all 4 of those parentheses. So a parentheses for the numerator, negative 6 natural log of 5. Actually, I'm hitting double keys for some reason. Parentheses for the numerator, negative 6 natural log of 5. Close the parentheses on the natural log. Minus 4 natural log of 3. Close the parentheses for the log. Close the parentheses for the numerator. Divide. Open parentheses for the denominator. 2 natural log of 3. Close the log. Minus the natural log of 5. Close the log. Close the denominator. And enter. Our solution for x is going to be negative 23.905. Negative 23.905. And we have our solution. A very short video today because really all these problems solve with the same general pattern. We just want to get used to taking the natural log of both sides in order to find our solution. So take a look at the homework, practice, 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 and come to class with questions. We will see you then. Section 4.4 starts taking a look at how we can solve equations with logarithms. Yesterday we took a look at how we solve exponential equations by using logarithms. Today we're going to have logarithm equations that we're going to have to solve by using exponents. But before we get too far into this, we first should address the little issue about domain and logarithms. If log base a of x equals b, then we have a restriction on the domain that x has to be greater than or equal to 0. Actually, no, I'm going to change that. It just has to be greater than 0. It can't be 0 at all. In other words, we cannot have a negative number inside of a logarithm. And that's something we're going to have to check with every one of these log answers, is does it make it so that we have a negative inside the log? In fact, let's write that down. This means we must check our solutions. So with that in mind, let's take a look at solving logs. Two major strategies in solving logs. The first major strategy we use is we write the problem as a single log, and then convert the log to an exponent. For example, if we have log base 6 of x plus log base 6 of x plus 1 equals 1, and we want to know what x equals. Well, we know that two logs added together means we really multiply inside the logs. So we can combine this to log base 6 of x times x plus 1 equals 1. We've now written it as a single log, so we can convert it to an exponent where the base of 6 to the first power equals the x times x plus 1. Well, 6 to the first is just 6, and so now we have something that's going to be really easy to solve. We distribute first to get x squared plus x. We'll subtract 6 from both sides to get 0 equals x squared plus x minus 6. We know now we have to factor, so we have x plus 3 and x minus 2. And then when we set each equal to 0, we get our solutions are x equals negative 3, and positive 2. The only thing we have to be careful of when we have a solution is go back to the x and the x plus 1. Both of these have to be positive. Notice if we plug the negative 3 in, we would be taking the log of a negative number. And that just doesn't work. If we plug the 2 in, the log of 2 is, well, that 2 is a positive. The x plus 1, 2 plus 1 is 3, also positive. So the 2 works, the 3 does not. So 2 is our only solution. With logs, sometimes we'll have one solution, sometimes we'll have two solutions, sometimes we'll even have none solutions. So make sure you're always checking your solutions. We cannot take the log of a negative number. Be careful there, that does not mean if the solution is negative we have to delete it. That's not the case at all. We don't throw out the negative 3 because it's negative. We threw out the negative 3 because when we plugged it back in, it gave us a negative inside of a log. And we're going to see a few problems on the assignment and today where the negative is good and the positive is bad. Plug it back in. Does it make us take the log of a negative number? That's what's not allowed. How about this? Let's do log base 3 of 2x minus 4 minus log base 3 of x plus 3. And we're going to make that equal to 2. Again, we're going to make this into a single log so we can convert it to an exponent. With subtraction, we know that turns into a single log base 3 that has division in it. The 2x plus 4 in the numerator and the negative log, the negative exponent means the x plus 3 is in the denominator, is equal to 2. Now that we have a single log, we can convert it to an exponent. 3 squared equals 2x plus 4 over x plus 3. And 3 squared, we know that is 9. And so now we can solve this simple problem by clearing the fraction, multiplying by x plus 3 on both sides. And when we distribute, we have 9x plus 27 equals 2x plus 4. Get the x's on one side by subtracting 2x, everything else on the other side by subtracting 27. And that's going to give us 7x equals 4 minus 27, negative 23. And when we divide both sides by 7, we get x equals negative 23 sevenths. Of course, we always want to check our answer. And if we plug negative 23 sevenths into the first log, multiplying by 2 is going to still be negative, and subtracting 4 is going to make it even more negative. When we plug negative 23 sevenths in, that first log becomes a negative. We have to throw that answer out, and this one actually has no solution. Because that first log ended up negative. The second log would have ended up positive, but the first one ended up negative. It's outside of the domain. So that's the general idea to the first strategy to solving logs. We write as a single log and convert it to an exponent. And with all of our problems, you always want to check your solutions. Our second strategy is if log base A of B equals log base A of C. We've got a log on both sides, then the insides, then B equals C. This is kind of like saying if the bases are both equal, then the exponents are both equal. This is exactly the same process. So if we have log base 3 of x equals log, whoops, helps if I copy the right problem. How about, let's try this. Log base 3 of x plus log base 3 of x minus 3 equals log base 3 of 4. Again, addition tells us that we need to write this as a single log that's multiplied together. So log base 3 of x times x minus 3 equals log base 3 of 4. Notice both sides have the same log base. If those bases are the same, then the insides must be equal. And if we distribute, that gives us x squared minus 3x equals 4. Subtracting 4 from both sides gives us x squared minus 3x minus 4 equals 0. And we're well on our way to solving by factoring to x minus 4, x plus 1. And of course then x equals positive 4 and negative 1. Plugging 4 in, the log of 4, that's a positive. 4 minus 3 is 1. The log of 1, that's a positive. 4 is good. But if we plug the negative 1 in, you see it makes both of those negative. And that's going to be no good, so we do have to throw out the negative 1. Because we cannot take the log of a negative number. So our only answer for this one is x equals 4. Let's try one more of these. Let's do the natural log of 2 minus x plus the natural log of 5 minus x equals the natural log of 18. Again, this one has a plus in the middle. That means we're going to multiply them together. And let's just go ahead when we multiply them together. FOIL, 2 times 5 is 10, minus 2x minus 5x plus x squared equals the natural log of 18. In fact, let's simplify in the middle there. 2 minus 5, 2 negative 2 minus 5, that's negative 7x. So that was just all of that distributing is what we did. Now we've got the same base on both sides. Remember, natural log means base e. If they've got the same base, then the inside stuff must be equal. 10 minus 7x plus x squared must equal 18. Making it equal to 0 by subtracting 18 from both sides. We'll also put it in order as we do this. X squared minus 7x minus 8. Factor. X minus 8, x plus 1 equals 0. Set each factor equal to 0, and x equals 8 and negative 1. Of course, we need to check these answers, and notice this time when we plug the 8 in, 2 minus 8 is negative 6. 5 minus 8 is negative 3. Both of those logs have negatives in them. We cannot have a negative inside a log, so the 8 gets thrown out. However, when we plug negative 1 in, 2 minus negative 1 is a positive 3. And 5 minus negative 1 is a positive 6. Negative 1 is a good answer because it doesn't make the logs negative. Notice here in this problem the positive answer was thrown out and the negative answer was saved. We don't necessarily throw out an answer because it's negative. We check the answer and throw it out if it makes the log negative. We don't care about x, it's the log. The log cannot be negative. So those are our two general types of strategies to solve with logarithms. We'll make them a single log and convert to an exponent, or if we have two equal logs with the same base, we'll make the insides equal to each other. From there we can only really do variations on a theme, and one such variation would be if the problem was quadratic in form. For example, if we've got log base 3 of x, and that is squared, minus 5 log base 3 of x plus 6 equals 0. Notice first that squared is not inside the log, so we can't pull it out front. There's a difference between the log base 3 of x squared, where the squared can move out front, and the log base 3 of x, and the entire thing is squared. We're squaring the log, not the x. So the exponent cannot move out front here. What I do notice is we've got this log base 3 of x, where one of them's squared, one of them's not. This is essentially quadratic in form, so we can factor it where log base 3 of x squared is log base 3 of x times log base 3 of x. And 6 is negative 2 and negative 3, which then gives you that negative 5 in the middle. So now all we have to do is set each factor equal to 0. In the first factor, we add 2 to get log base 3 of x equals 2. In the second factor, we add 3 to get log base 3 of x equals 3. And now we're back to where we started at the beginning of this video. Change the log to an exponent. 3 squared equals x, or x equals 9. 3 cubed equals x, or 27 is equal to x. Check in the original, both of these keep it positive because it's just the log of x. Both these solutions are going to work for this problem. Sometimes quadratic in form can become very interesting to us when we start looking at trying to get the same base. Let's start with this problem first. Let's do 10 log base 4 of x minus 3 log base 8 of x equals 4. Both of these have different bases, so we're not going to be able to combine them and work with them unless we were to change these to have a common base. With 8 and 4, if we were talking about exponents, 8 and 4 would have a common base of 2. 4 is 2 squared, and 8 is 2 to the 4th, or 2 to the 3rd. So we are going to use the change of base formula. Remember, the log base a of b is equal to the log base, our convenient number, base c, of the inside divided by the log base c of the old base. Here, our 4 and our 8 would probably be best served with a base 2. So we have 10 log base 2 of x divided by log base 2 of 4. Minus 3 log base 2 of x over log base 2 of 8 equal to 4 still. Now that 4 and 8, let's rewrite them with exponents. 4 is really 2 squared, and 8 is really 2 cubed, because that's going to allow us to simplify using our property that the log base a of a to the x, if the bases match, the solution is the exponent. So now we have 10 log base 2 of x divided by, bases are the same, so the answer is the exponent, 2. Minus 3 log base 2 of x divided by, the bases are the same, so the answer is the exponent, equals 4. Well, this just keeps getting nicer because now those 3's divide out, and 10 over 2 reduces to 5. So we really have 5 log base 2 of x minus a log base 2 of x equals 4. We can do this a couple ways. We can make this x to the 5th and then change it to a division problem. Or we can say 5 minus 1 log is 4 log base 2 of x's. which is equal to 4. And then I'm going to divide both sides by 4, which gives me the log base 2 of x is equal to 1. Now all that's left is to convert this to an exponent. 2 to the first power equals x, or simply 2 equals x. We've got our solution. And what made this problem work was we identified a convenient common base so that we could start working with the logs together as a group. So if we've got different bases, we're going to have to do some work to get the same base. This first example, we looked at the base 4 and the base 2 and said, hey, the common base is a base 2. Sometimes it's not as obvious what the common base is. Sometimes we're working with a problem like log base 2 of x plus log base x of 16 equals 4. Here we've got a base of 2 and a base of x, and we really have no idea what the common base is for both of them. My recommendation in this case would be let's go with the number, not the variable. Let's do a log base 2. So we're happy with the log base 2, the first one. The second one, though, the log base x, is going to need some work. So we've got log base 2 of x plus, changing it to a log base 2, we keep the 16. We just have to divide by log base 2 of the old base is equal to 4. Now here I don't like that fraction. So let's get rid of the fraction by multiplying each term by log base 2 of x. And when we do, the fraction divides out, and we have log base 2 of x times log base 2 of x. Well, that's log base 2 of x squared times itself. Plus log base 2 of 16. Well, gee, let's actually play with 16. Let's factor it. 16 is 2 to the 4th power, which means this is going to simplify to 4 in a minute. That's going to be nice. Equals 4 log base 2 of x. And what you notice we have again is we've got that log base 2 of x, one time it's squared, one time it's not. We're quadratic in form. Let's make it equal to 0 by subtracting 4 log base 2 of x from both sides. Log base 2 of x squared minus 4 log base 2 of x plus, remember if the bases match, the answer is just the exponent, equals 0. And now we're ready to factor this expression. Log base 2 of x squared is log base 2 of x times log base 2 of x. 4 is 2 times 2, and they're both negative. So that means they're both actually the same factors, so we're just going to do this once instead of twice. Log base 2 of x, add 2 to both sides, equals 2. Change it to an exponent, and 2 squared equals x. So that means x is equal to 4. Double check that doesn't make any negative logs, so we have our solution, x equals 4. This last part is really just variations on a theme, though. Our basic strategy for solving these logs is always going to be the same. If we have logs on one side, we'll write them as a single log and convert them to an exponent. If we have logs on both sides, we'll write them as single logs on each side. And since the bases are equal, the insides are equal. The variations that we looked at said, hey, if it's quadratic in form, we can factor it. If we have different bases, we need to get a common base or a convenient base, and then we can solve from there. Take a look at the homework, and we will see you in class. This video is going to take a look at applications of logarithms and exponents. And the main application we're going to look at is going to center around the basic exponential equation. And that is going to be the function f of t is equal to p e to the kt. Now each one of these variables is going to mean something to us. The p is what we call the present value. Another way of thinking about it is where you start. The e, we've already seen that as Euler's constant, is approximately equal to 2.718, and that's that e natural base for our natural log that we've talked about before. K is the growth or decay constant. And finally, t, the variable we're usually most interested in working with, is the amount of time that's going by. So, for example, I might be asked to find out how long will it take an investment to quadruple. At 8%, compounded continuously. Well, we've got some type of starting amount that's going to need to quadruple. So we're going to go from some principal amount, and we want it to quadruple to 4 times that principal amount. So 4 times the principal amount is how much we have at the end. The principal is what we start with. E to the k, the constant of growth, it's 8% growth continuously. So 8% is 0.08. And t, we're solving for the time. Well, before we can change anything to a log, we need to get the exponent part alone and by itself. So we'll divide both sides by p. And in fact, those p's all divide out, and we just get 4 equals e to the 0.08t. And what's nice here then is we can convert this to a log problem. We know it's a natural log with a base e of the 4 would equal the exponent of 0.08t. All we have to do to solve for t to get the time alone is divide by 0.08. And now we'll know how long it's going to take by simply doing the natural log of 4, closing the parentheses, divided by 0.08, we get 17.34. 17.34 years. Any investment at 8% will quadruple every 17 years. Let's take a look at another application. The Moses Lake population has grown 1.8% per year. To 20,305 in the year 2014. What was the population in 2000? Well, we know f of t is equal to pe to the kt. Looking at what we have, the 1.8%, that's going to be our k as a decimal 0.018. 20,000, that's the starting value that we're given, our P, in the year 2014. Now we could make the time 2014, but that usually makes it a bit more difficult. So let's call that our 0. Year 0 is when the population was 20,305, and then we'll use our time to say how far away from 2014 we are. So the question's asking about the year 2000. So for our time, that's 14 years ago. We're going to use negative 14 to represent that 14 years ago. And so now we have f of negative 14 is equal to the principal value, the present value, which we know, of 20,305, times e to the k, which is 0.018, times t, which is negative 14. Our calculator now can do the work from here. 20,305 times e, which is second ln, raised to the 0.018 times negative 14, and we get 15,782, let's round it, 15,782 was the population in the year 2000. Let's look at another application, one that gets used a lot for this exponential equation, PE to the KT. And that is this concept of half-life. The half-life of titanium 44 is 63 years. How much of a 52-gram sample is left after 46 years? So for those of you that haven't taken a science class with half-life in it, a little description of what half-life is. Half-life basically says if I've got this block of titanium 44 made up of all of these atoms that are just in here in a grid, all these atoms are locked together, and what happens is the electrons and the protons and the neutrons in there are all moving around. And sometimes what happens is a beta decay where it loses either protons or electrons or neutrons, and when it does that, it changes the type of element it is. It's a different element because it's got a different number of protons. It's called beta decay. What happens is there's a probability that any one of these will suddenly decay away at any given moment in time. So what happens is there's less and less titanium actually available. And the way the probabilities work out is it takes about 63 years and half of them are gone. Then it will continue to decay, and in 63 years another half of them will be gone. And then it continues to decay another 63 years, and another half of them will be gone. And then 63 years later, half of them will be gone. The idea is every 63 years, half of the elements, or half of the atoms, are gone. Essentially, after 63 years, there's a 50% probability the element has decayed away. That's half-life, when there's a 50% probability that the elements have decayed away. So what we need to know is what is the decay constant that corresponds with a 63-year half-life. If we start with P At the end of a half-life, there is 0.5 p remaining. Half of p. And our formula says we take the principal starting amount times e to the k t, and we know the amount of time it takes to get a half-life here, in this case, is 63 years. So again, we divide both sides by p to get rid of that p on both sides, and we have 0.5 equals e to the 63k. Change this to a natural log problem. Base e of 0.5 equals 63k. And we finally get the k alone by dividing both sides by 63. Our calculator then can tell us what the natural log of 0.5, close the parentheses, divided by 63, hit enter, negative 0.11. Constant is negative 0.011, sorry. This is the decay constant that corresponds with a 63-year half-life. Now that we know that 63-year half-life, we're ready to answer the question that's actually asked of us. How much of a 52-gram sample is left after 46 years? 52 is the principal that we start with. E to the k, which is negative 0.011, times t, which is 46 years. Put the calculator out of the way. Now what I'm going to show you is going to be a nice trick to use when the line above it has the k in it. You see the 0.011 right above where my cursor is. That's going to be important here as I type in 52, second e, and then I really want to put the k here. To grab that previous answer, I'm going to hit second and then the negative sign, which takes the previous answer. That way I don't get a round-off error, times 46. And when we hit enter, there's 31.35 grams of titanium 44 remaining of my sample. So I have 52 grams. 46 years later, it's probably going to be 31.35 grams. It decays away. This particular application is going to be important enough to us that we're going to do another example like it. How about this one? The half-life of the element fermium 253 is 3 days. How much of a 12-gram sample is left after 1 week? The first question we're going to have to attempt to solve is, what is the decay constant that's going to correspond with a 3-day half-life? So if we start with p, it's going to decay away to half of p, or 0.5p, when multiplied by e to the k t. The amount of time it takes to go from p to half of p is 3 days. Divide both sides by p to get 0.5 equals e to the 3k. Convert this to a natural log of 0.5. That's going to equal the exponent of 3k. And then get the k alone by dividing both sides by 3 on our calculator. So we have the natural log of 0.5, close the parentheses, divided by 3 is negative 0.231. Negative 0.231. Decreasing 23% per day, really. Now we're ready to actually answer the question. How much of a 12-gram sample, that's the principle I'm starting with, the present value, is left after 1 week? That's our time, but be careful not to put 1 in there. Notice the units on our half-life were in days. So t also needs to be in days. So we've got 12 e to the k, which is negative 0.231, or we're going to use the previous answer, times the amount of time, which is 7. So 12 e to the, notice that previous answer again, second negative sign gives me the previous answer, times 7. Enter. My 12-gram sample is down to 2.38 grams. 2.38 grams. After 1 week. This stuff is very unstable. It doesn't stick around very long. It decays away pretty darn quickly. So all these examples we've seen, population, continuous interest, half-life, doubling time, same idea, all use the same basic equation, PE to the KT, PE to the KT. There are equations, though, and problems, application problems, that are slightly more involved. More involved equations. And these equations I wouldn't expect you to memorize. Instead, I would give you these equations. And they just require us to know where to plug what and how to solve for what. One example of this is what is called the logistic equation. The idea behind the logistic equation is, let's say there's some population of animals that's growing in an environment. They can't grow indefinitely at the same pace. Eventually they'll run out of food, or they'll run out of water, or a predator will move in and take advantage of them. Basically, there's a maximum sustainable population in an environment for some organism. The further away they are from that maximum, the quicker they can grow, because there's lots of resources available. But when they start to get close to that maximum sustainable population, the population is going to start to level out and stop growing. There's an equation that models this. If you start with the population, call the starting population B for beginning population, with a growth rate of K and a maximum sustainable population of M for maximum, it grows over time. We'll use T for time, using this function. Q of T is equal to M over 1 plus B e to the negative K T. So if a population of sparrows grows at a rate k equal to 1.31, and we're going to say the population is currently 1,200, but the system can support 2,400, twice that. How many sparrows will there be in 7 years? So here we're given the constant for these sparrows and how they grow. We know the population is currently 1,200. That's the beginning population. And that the system can support 2,400. That's the maximum that it's going to be able to sustain. We're interested in when time climbs up to 7 years. So Q of t, Q of 7 is going to equal the maximum, 2,400, divided by 1 plus the beginning, 1,200, e to the negative k, 1.31 times t, which is 7. So plugging that in our calculator, 2,400 divided by parentheses 1 plus 1,200 e, which is second ln, to the negative 1.31 times 7, close the parentheses. Whoops. Make sure at this point you get out of the exponent. You might have to, depending on your calculator, close the parentheses on the exponent or scroll out of the exponent. Then close the parentheses on the denominator. Which is an interesting point that I didn't stress as I typed this in, is I need to make sure that denominator is in parentheses, so the calculator knows that entire thing is in the denominator. And what we find is there's about 2,133. 2,133 sparrows. So it's grown from 1,200 to 2,100. Maximum it's going to sustain is 2,400 over time. So that's one way I might be able to give you an equation that involves exponents or logs, and you should be able to figure out how to solve and answer the question. Let's look at one last problem before we wrap up our very last video for Precalculus. Newton's law of cooling. The idea is how fast something cools down is actually an exponential problem. Newton found out that an object at temperature T sub 0, starting temperature, initial temperature T0, surrounded by air temp of T sub A, let's do capital T, air temperature T sub A, will gradually cool to a temperature T over time, lowercase t. We're just going to try and confuse you with all these t's. Capital T sub 0 is your starting temperature. T sub A, that's the air temperature. Regular T, that's the temperature it ends up at. Lowercase t, that's the time. The formula is the final temperature is equal to the temperature of the air plus the temperature starting minus the temperature of the air times e to the k t. So if you leave a hot pizza at 350 degrees on the counter, where air temp is room temperature of 72 degrees, and the constant for this pizza is equal to negative 0.08. How long until the pizza cools to 100 degrees? Well, 350, that's the initial starting temperature of the pizza, so that's going to be our T sub 0. The air temperature is 72, that's our T sub A. We're told our K is negative 0.08, and we want the pizza to cool to a final temp, or T, of 100 degrees. So when we plug this into our formula, we get 100 equals the air temperature of 72 plus parentheses the starting temp of 350 minus the air temp of 72 times e to the k, which is negative 0.08, times t. Simplifying what's in the parentheses, 100 equals 72 plus 350 minus 72 is 278. E to the negative 0.08 t. What we're solving for again is in the exponent. And so to get it out of the exponent, we're going to need to write it as a natural log. However, we can't do that until that part is alone. We're trying to isolate the part with the exponent. So first we'll subtract the 72 from both sides to get 28 equals 278 e to the negative 0.08 t. Divide both sides by that 278, and e to the negative 0.08 t is equal to, let's just keep this as the fraction because the calculator is going to do the dirty work for us, 28 over 278. Converting this to a natural log, because we already have the base e of 28 over 278 is equal to negative 0.08 t. So to get t alone, we just have to divide by negative 0.08 on both sides. And now we will know our time when we type this into our calculator. Natural log automatically opens up parentheses, 28 divided by 278, close the parentheses, and then divide by negative 0.08, hit enter, and we get 28.7 minutes. So this pizza at 350 degrees, in 28 minutes will cool down to a mere 100 degrees. Again, these more involved equations I don't expect you to memorize, but you should know how to do how to use them. In addition, you should also know the basic exponential equation. You should be able to use it for interest. You should be able to use it to double or triple or quadruple your money. You should be able to use it for half-life. And you also should be able to use the equations I give you. So take a look at the homework assignment. It's our last one for Pre-Calc 1. We will see you in class tomorrow.